Ready to dive deep. Today we're taking on hidden particles, the ones physicists are just dying to find.
And we've got a great map for this deep dive.
Our source material.
Effective limits on single scalar extensions in the light of recent LHC data.
Okay, gotta admit, that's a mouthful. But it's all about using the Large Hadron Collider to figure out what's beyond the standard model, right?
Exactly.
Which, for anyone just joining us, the standard model is like our current best guess at how the universe works at the tiniest level. It's got all the particles, all the forces.
So it's got holes.
Yeah, like dark matter doesn't explain it. Why there's way more matter than antimatter, another head scratcher.
This paper dives into 16 different ways we could fill those gaps.
16. Okay, lay it on me.
Each one adds a new kind of particle, a scalar particle. Think of them like spin-offs of the Higgs boson.
The Higgs, right,
Yeah.
the one that gives everything mass. Okay, so we're adding new particles, but they have to be scalar. What makes them different again?
Spin. Other particles, like electrons, they have it. Scalar particles, nope. The Higgs boson, that's the most famous scalar particle.
So it's like we're saying, what if the Higgs has a whole family we haven't met yet?
Exactly. And more importantly, could those family members exist without messing up everything we already know about physics?
Which is where the LHC comes in, smashing those particles together to see what shakes loose.
And they're using this really cool technique called effective field theory, EFT.
EFT. All right, you got to break that one down for me.
Imagine you're trying to figure out, I don't know, how a whale affects a lake.
Mm.
You can't actually see the whale itself.
Okay, I'm intrigued.
You'd look for the ripples, the changes in the water, the missing fish.
So you're looking at the effects to understand the thing you can't see directly.
Exactly. And that's EFT in a nutshell. It lets physicists see the influence of these maybe really heavy hidden particles without needing to actually create them in the LHC.
Which is probably a good thing, because creating those particles is no walk in the park, right?
Not even close. So instead, we look for their subtle hints, the way they affect what we can see at the LHC.
Makes sense. So we're not just blindly smashing stuff together. We're looking for very specific clues.
Absolutely. Things like how often the Higgs boson is produced, how it decays. Anything different from what we expect could point to hidden particles messing around behind the scenes.
It'd be like the Higgs suddenly acting out of character. Wait a minute, something's making me do this.
Right. They're also looking at what happens when the LHC smashes protons together and makes these pairs of force-carrying particles. We call them bosons.
So like a subatomic car crash, and we're combing through the wreckage.
Looking for anything weird, especially in the energy and angles of those bosons. Even tiny differences from what the standard model predicts could mean, hey, new physics alert.
I'm picking up what you're putting down. Okay, so they're looking at the Higgs, they're analyzing these boson smash-ups, all to test out those 16 scenarios for new particles.
And each scenario is different. Some have these particles called color singlets, others have color triplets. It's a whole zoo of possibilities, each with its own fingerprint.
So it's like they're playing 16 rounds of particle physics Clue.
And to make it even more interesting, they dive deep into two specific scenarios just to show how this all works.
Oh, now you've got me hooked. What are these prime suspects? Spill the tea.
First up, the extra Higgs doublet. What if, and this is where it gets really cool, what if the Higgs boson has a secret twin?
Double the Higgs, double the trouble. What's our other suspect?
This one's a doozy, the leptoquark.
Lepto.quark. Okay, before we go any further, I need a quick reminder. Quarks, those are like the building blocks of protons and neutrons, right?
You got
And leptons are.
a whole other category. Think electrons, neutrinos.
Okay, right. So what makes this leptoquark so special?
It can interact with both quarks and leptons.
Whoa, this particle plays for both teams.
Exactly. And that's a big deal because it could be the key to understanding some big mysteries, like why neutrinos have mass. The standard model really struggles with that one.
Okay, I'm getting some serious cosmic detective vibes here. But they're not just relying on the LHC for this, right? You mentioned computer programs.
Oh yeah, they use some serious computing power. One program they used is called Codex. It simulates what we'd expect to see at the LHC if these new particles were real.
So like a virtual universe inside a computer?
You got it. And here's the really wild part. They're not just plugging in basic physics. They're taking into account the weirdness of quantum mechanics.
Because in the quantum world, anything goes, right? Particles acting like waves, being in multiple places at once.
It gets pretty strange down there. And to really make sense of it, we need to take a trip to the next level.
Last time we were talking about hidden particles, these like secret ingredients in the universe's recipe. We've got our prime suspects, the extra Higgs doublet, and the leptoquark. Did our physicists actually find them?
Well, it's not quite that simple. Think of it more like narrowing down the possibilities.
Okay, so no smoking gun, but they're getting closer.
Exactly. We're talking groundbreaking stuff here. The LHC data, it puts tighter constraints on these hypothetical particles. It's telling us more about what they can't be, which is huge.
So less, here's the particle, and more, don't bother looking here.
You got it. It's incredibly valuable because it guides future searches, helps physicists refine their theories, focus their experiments.
Okay, that makes sense. No more searching the entire universe for one tiny particle. So how'd they actually analyze the data? We talked about the Higgs boson's behavior, those boson smash-ups. What were they looking for specifically?
One of the big ones was something called electroweak precision observables. It sounds complicated, but really, it's just super precise measurements of how particles interact through the electroweak force.
Right, the electroweak force. That's like dot responsible for radioactive decay, stuff like that. And you're saying even tiny differences from what we expect could mean something new is going on.
That's the idea. Imagine you're trying to balance a scale perfectly. Even a tiny, tiny speck of dust could throw it off. They're looking for those specks of dust in the electroweak force. On top of that, they dove deep into Higgs boson measurements, breaking down how they're produced and how they decay into these categories called, get ready, simplified template cross-sections.
Simplified, template, cross-sections. Okay, you lost me.
Basically, they're looking at the Higgs boson's entourage. Like, what other particles are hanging out with it when it's born?
So it's all about who the Higgs is seen with, like its social circle.
Exactly. By comparing the rates of these different Higgs hangout groups with the standard model, any surprises could point to hidden particles.
Gotcha. Cosmic detectives checking the guest list for the subatomic party. And speaking of suspects, we had those two big ones, right? The extra Higgs doublet and the leptoquark. Any luck there?
Let's start with the extra Higgs doublet. The data, it put some serious limits on its properties.
So no more hiding in the shadows for this extra Higgs.
Not so fast. It's more like they narrow down the possibilities. Some types of extra Higgs doublets ruled out, but others could still be out there, just hiding really well.
Okay, so the extra Higgs is still in the running. What about our friend the leptoquark?
That one's trickier. Remember, it interacts with both quarks and leptons, so its effects are harder to pin down. It's like trying to catch a shadow.
But they haven't given up hope, right?
Absolutely not. They were able to set some crucial limits. For example, if leptoquarks exist, their mass and how strongly they interact has to fall within a certain range. Otherwise, we would have seen them by now.
So another win for the LHC detectives. What's next?
Well, the LHC is still collecting data. That means more clues, more ways to refine our search.
It's like we're getting a clearer picture of the subatomic world with every experiment.
And that's what's so exciting about this paper. It shows how physicists are pushing the boundaries. They're not just waiting for discoveries to fall into their laps, they're actively seeking them out. But there's one more piece to this puzzle we haven't even touched on yet, that quantum weirdness we mentioned.
Quantum weirdness, right. We left off on a cliffhanger last time. You were about to blow my mind with the really strange stuff.
All right, you ready for this? We talked about those computer programs, how they simulate LHC collisions with all those hypothetical particles. Well, it gets even wilder. They brought in something called renormalization group equations, RGEs for short.
RGEs. Okay, that sounds like next level physics jargon. You're going to have to break that one down for me.
Okay, so imagine looking at a river from far away. It all seems pretty simple, right? One smooth flow.
Makes sense.
But what happens when you get closer?
You see more details.
Exactly. The currents, the little eddies, how the water interacts with the riverbed, RGEs. They're like that close-up view for particle physics. They show us how interactions between particles change depending on the energy scale.
So it's like the rules change depending on how zoomed in you are.
That's a really good way to put it. And just like those close-up details tell you more about how a river shapes the landscape, RGEs give us a more precise picture of particle interactions, especially at the crazy high energies we see in the LHC.
Okay, I think I'm following. But how does this help us find hidden particles?
By incorporating those RGEs, the researchers made their LHC predictions way more accurate.
Ah, so it's like upgrading their detective's toolkit.
Exactly. They get a much clearer picture of how those hidden particles, if they're real, would actually show themselves.
So they're making sure they don't miss any clues, no matter how subtle. Clever. Did they put these RGEs to the test?
They did. They focused on that extra Higgs doublet scenario we talked about. Ran the numbers with the RGEs and without.
What happened?
Night and day. The RGEs, they ruled out even more possibilities, like using a microscope instead of a magnifying glass.
So even more precise. But you also said these RGEs, they don't just refine predictions, they create entirely new ones. What did you mean by that?
Right, so with the extra Higgs doublet, the RGEs actually predicted some brand new effects, things we should be able to see in the LHC data if these particles are real.
Wow, so it's not just about eliminating suspects, it's about uncovering new clues we didn't even know to look for.
Exactly, and that's what I find so exciting about this research. Even if they didn't discover these hidden particles outright, they moved us so much closer. We have a better idea of where to look, what to look for.
It feels like we're on the verge of some major breakthroughs.
I think we are. It really highlights how science works. We'll keep exploring, refining our theories, testing our ideas, and sometimes we stumble upon something amazing along the way.
The universe is full of mysteries, but we're slowly unraveling them one by one. And who knows? Maybe our listeners will be the ones to unlock the next big secret. Thanks for joining us on this deep dive, and keep those questions coming.